Hi, my name is Justin Au.
Hello, my name is Hagen Fritz.
Hello, my name is Daniela Benitez.
Hi, my name is Maria Gonzalez.
And this is the analysis of our landfill remediation alternatives.
So first we're going to start with the required alternatives for remediation of the landfill site. Our first alternative is the simplest, and that is to do nothing. From figure 1 we can see we have flow from the northwest to the southeast as flow goes perpendicular to the contour lines, which are pictured in blue. And we know this is a problem because there is a landfill in the area directly where the flow would come through. And this is a problem because leachate from the landfill has infiltrated the local stream, which has been causing problems for some neighbors, as they've been complaining about respiratory problems, nausea, dying vegetation in the area, and odors emanating from the site. This slide shows the mass balance from our do-nothing alternative. In the bottom right we can see the outflow to the river is about 0.161 feet per second, and our percent discrepancy for this simulation is 0%, so we can be very confident that the simulation we ran is correct. And so this mass balance will function as our base case, and so we want to reduce the amount of flow we have to the river. So anything less than 0.161 will be a success because all the flow that's going to the river is carrying the leachate from the landfill, and we don't want this leachate to go into the river. This slide shows the hydraulic head profile for alternative A, and this profile is from slicing the figure on the right directly down the middle along column 25 from the bottom all the way to the top. So at the bottom we have somewhere around 102 feet for our head, and at the top it goes to nearly 116. Since our head is higher on the northwestern side and lower on the southeastern side, that means flow is going to go from higher head to lower head, and hence why we're having this leachate problem.
Moving on to alternative B. This includes a placement of an impermeable cap. The flow in this alternative is exactly that of alternative A, flowing from northwest to southeast. However, the cap does reduce the recharge of the river over the landfill. This is our mass balance for part B. As you can see, the outflow to the river is 0.1614, and the percent discrepancy is 0, meaning it's accurate. This is the hydraulic head for alternative B, which closely resembles the hydraulic head of alternative A. So we compared alternative B with alternative A, and not very many things changed, and if it did, it changed ever so slightly. So there were slight differences in the head profile along the vertical center of the site. The cap did not significantly reduce the flow from the landfill. As you can see, the outflow was still 0.1614. However, the recharge of the landfill was reduced a little bit.
Here we have alternative C, where we continue with the impermeable cap and add a confining wall. Because of the confining wall, we are able to reduce the flow, and we are able to direct the flow away from the landfill. The wall itself has a hydraulic conductivity of 4.92 e to the negative 10. This is a mass balance for alternative C. You can see that our flow to the river decreased to 0.1442, and then but the percent discrepancy increased to 0.59. Although it increased, we are able to see that it is still relatively accurate due to the fact that it is below 1. Here is the hydraulic head graph for alternative C. As you can see, there are two plateaus that occur due to the fact that there is a wall that is greatly affecting the head. As you can see in the comparison of alternative C to A and B, the outflow to the river was reduced by 0.0172. The wall boundary really seems to be effective and an effective means of reducing the flow.
For alternative D, we kept the cap and walls and added a drain, which is represented by the yellow cells. The drain is at an elevation of 100 feet. We found that at this elevation, the percent discrepancy remained below 1%. Changing the location and the drain elevation was a challenge throughout because at different elevations, the percent discrepancy got really high at about 10%. Adding the drain in general helped reduce the flow significantly, and you can see a change in the contours, especially near the drain location. Here's the mass balance for alternative D. We can see that the river outflow has been reduced to 0.1092, and our percent discrepancy is negative 0.93. This is below 1%, which we are considering acceptable. So this is the hydraulic head profile for alternative D. You can see that it is very similar to alternative C. It is the head profile along the 25th column.
In comparison of alternative D with A, B, and C, you are able to see that alternative D has the lowest amount of outflow to the river. The addition of the drain to each of the alternatives reduces the amount of flow and contamination going to the river. The drain decreased the flow by the most significant amount out of each of the alternatives.
We now move on to our suggested alternatives. So our goals for the alternatives is to use the combinations of walls, wells, drains to limit the river outflow. We don't want to limit it to 0 because we want the river to still continue to flow, but we want to keep the percent discrepancy of the outflows to below 1%.
For alternative E, we decided to try an extended drain. So the length of the drain is 1,300 feet and the area covered by the drain is about 13,000 feet. The drains lie at an elevation between 101.5 feet to 101 feet. This difference in elevation is to keep the percent discrepancy low. The drains are sensitive to the elevation at which they are at. This is the mass balance for alternative E. We can note that the river outflow here is 0.1295 and that the percent discrepancy is negative 0.88. This is less than 1% and therefore we are considering it acceptable. This is the hydraulic head profile for alternative E. You can see that it is different from those that you've seen before for D and C. This head profile resembles alternatives A and B's head profile the most. And again, it's for the 25th column.
Our second alternative is including a diverting wall to that extended drain in alternative E. We're going to reduce the drain from alternative E by 200 feet and move it up by 100 feet and then to the right 700 feet. And above that we're going to include a diverting wall of 900 feet in length. And the idea here is to divert more of the flow to the drain. And the drain has an elevation varying from 102 on the far leftmost side to 101.5 feet on the farmost right side. Here we see the mass balance from alternative F. We can see we have a good reduction in flow to the river. It's at 0.125 feet per second, and our percent discrepancy is getting close to the 1% mark, but it's still beneath it at 0.97. Lastly, we have the hydraulic head for alternative F. You can see it matches similarly to the ones in alternative A, B, and E, as we don't really change anything along that line on the 25th column.
This is another one of our suggested alternatives, which is alternative G, which includes a confining wall, a well, and a drain. So we use the basis of alternative C and use the exact same confining wall, but we added a pumping well on the inside and a drain on the outside. The pumping well rate on the inside is -0.1, and then the drain has a length of 500 feet and an area of 5,000 feet. As far as looking at the mass balance for alternative G, we are able to see that the river leakage, which is the flow to the river, is 0.1146, and the percent discrepancy is -0.93, which is still below 1, which allows us to have an accurate reading. When looking at the hydraulic head graph for alternative G, you are able to see that the head also plateaus at a specific point due to the wall, which is consistent with the results from alternative C.
On the right of this slide, we can see the comparison between all the alternatives, A through G. We can see that alternative D had the highest reduction in flow to the river at 0.1092 feet cubed per second, whereas the alternative B had the least reduction of flow and actually did not improve over our do-nothing alternative. And alternative A actually is the cheapest option, while alternative G, possibly alternative G, is the most expensive option, since we are adding in wells, walls, and pumps to these options over alternative A, which we are adding nothing.
Our recommendations would be alternative D and G. So considering the flow of the river, alternative D provides the greatest reduction in the flow over the landfill. And coming from a financial point of view, alternative A is the most economical. However, this does not solve any of the problems that we currently have, and that's why we are running these alternatives. So we believe the best option to reducing the leachate flow into the river is either alternative D or G.